right, shall we start? Okay, cool. So, today we will be covering recursion. And before recursion, first we are going to take a look at function calls. Like what happens once we start executing program starting from the main function for many languages. And then how things evolve as we execute statements one by one. So, let's start with a makeup example. Let's say we have the main function. And here first we call function A with parameters, or like function f1 with parameters a, b, and then function f2 with parameters c, and then function f3 with parameter d. And also, let's do this. Let's also give definition for function f1. Oh, let's make it void. F1. And let's call F2. Let's also call F3 with E2 plus 1. All right, so our example is ready. Like, once we start executing a code, what we do is we start from main function, right? So, in this case, we will start executing from the first statement in the main function, which is creation of node B. So what this will do is, like we have the space of main in our memory. And like it is gonna create the B node reference pointer, and then it's gonna go right. Let's assume like this has a constructor function. It gets the value for the data and then place the value for the data into data field in our node object. For the sake of simplicity, I'm just gonna write the data inside of the node object. Okay. So in reality, what this means is like we have here data field, and then we actually write 100 inside of it. Okay? And please feel free to cut me and ask any question if something is not clear, because you need to have the complete story in your mind clearly so that you understand function call logic as well as recursion logic. Okay? So, after first statement, we are going to execute the second one. And here, the second one is a primitive type. It's an integer. And we initialize it with value 5. And after that, we actually have a function call. So, whenever a function call happens, the previous state of the previous function or the caller function is added to call stack. So here, this main guy, let's say we represent this with M, and this is the first time we are coming out of main. Let's represent it with M1. M1 is placed at the bottom of the call stack. Okay? So we get everything that is in the main function. It's as if like you have a food on the plate and then you put injera on it and grab it and put to the call stack. And after that, since we make a function call, the new guy is going to come into call stack, which is F1. Let's say F1, since we are calling it for the first time. Oh, it's small one. Or let's represent them big numbers, F1, big letters. F1, this is the first time we are calling it. So, let's see what's going to be in F1. Like F1 gets two parameters. The first parameter is an integer. And since integer is a primitive type, what happens is the value is directly copied. So the value is 5 here, right? And here we have I1 box for F1 call, and we copy the value from the parameter into this I1. Like the parameter is A. That's why we copied this 5 here. So we have 5 written in I1. And we have second parameter, like which is a reference, like which is a pointer. Therefore, it's a complicated type. It's not a primitive type. Instead of copying everything that is in the area that is pointed by this pointer, what we do is we just copy the reference. So here we have an pointer, right? And this guy starts pointing the same place. Like the reason is, imagine, this is a complicated type. We don't know how big it is. Maybe this node object has 20 megabytes of information in it. If we make the copy every time we make a function call, this is going to be super inefficient. So that's why these complicated types are copied by reference, meaning the data is not copied. And we have a reference that is pointing to the same data. Or with the jargon of C++, we have a pointer that is pointing to the same location. So what is the difference between copying the data and just copying the reference? The difference is, once we copy the data, if we manipulate that data, it's not going to change the original value. Because we are talking about two distinct places in the memory. Once you modify one, the other one is not going to be modified by itself. However, once we pass by reference, as in the case of complicated types, whenever we modify things through n, it is going to update what we have here in B. Okay? So this is a very important difference, and you should be very clear about that. Like in many different languages, the implementation is the same way. Like they, if it's a primitive type, they copy the value And whenever you make modification, it's not going to affect the original one. But if it's a complicated type, since it does the copy for the reference, but in the end they are both pointing to the same location in the memory, whenever you make a modification inside of the function call, it is going to actually update the original value. Okay? So, it's going to be more clear once we execute on our example. So far, like we execute up to here. And now we created this f1. And we initialized our variables for the f1, our parameters for the f1. Okay, so what f1 does is it actually makes two more function calls, right? And since it is making a function called f2, we are going to create a new state for f2. And this is the first time we are calling f2, so I'm going to name it as f21. And we call this guy with I1 plus 1. So f2 gets a parameter named in. It's an integer, so it's a primitive type. That's why we are going to have, we are going to copy the value. So here, the value of I1 was 5. And we call the function with I1 plus 1. So we are going to call this guy with 6. And in f2, what we are doing is we are just printing to the screen the input that we get. And here, what is going to be printed to the screen is, let's say this is our screen. First we print the value in the in variable, which is 6. So f21 is also called. That's why it's going to be in our call stack too. And once the execution of f2 is finished, once we are done with this statement, obviously there is hidden return for the void functions, right? So we are going to return back to our caller. And once we are returning, our function state is going to be taken out of the call stack. So we're not going to have f21 anymore in our call stack. So now we get rid of this guy. We are back to f1. And we finished executing the first statement in f1. Now we progress with the second statement in f1, which is a function call for f3. And this time we pass our parameter directly, as it is. So what happens is, again, since this is the first time we are calling f3 function, I'm going to name the state of the function as f31. And inside, so let's make it a little bigger. And inside f3 we have only one parameter, which is a reference or pointer. And since it's a complicated type, again, the data is not copied, so the reference is copied. The pointer is copied. So we are going to start pointing to the same location. And in F3, we are actually manipulating the data that is pointed by our parameter n. And we say plus plus. So what happens is, this 100 becomes 101. And then we print it to the screen. So at this point we are going to be printing 101. And here right now we have F31. Sorry, okay. F31. Once F3's execution finishes, we get back to our caller, which is F1. And this comes out of the call stack. And since this was the last call for F1, we return from F1. So F11 also goes out of stack. So we don't have this guy and this guy anymore. Because whenever we are done with the function, we just drop everything about that state. Because we don't need it anymore. I mean, we might create it again if there is exactly the same call. But since we don't know whether it's going to happen or not, we just get rid of it. Because otherwise we can waste tons of memory. Like if we keep track of everything that we have done, and just in case we can get back to it with the same call, we are going to be wasting a lot of memory. So that's why whenever we are finished with one state, it's just deleted from the memory. And finally, we get back to our main function. So now we make two more calls. We call F2 again. this time directly from main. Since this is the second time we are calling f2, I'm going to name it as f22. And we pass a as parameter to f2. f2 gets one primitive type parameter, which is in. So we just copy the value of 5 into f2, which is going to be 5 here. Or actually, like, if we add this statement here, it's going to be nice, let's say in plus plus, to see the difference between this one and this one. So now we get the input value as 5 for in, and then we execute in plus plus. Now this guy becomes 6. And then we print it to the screen. So we write another 6 to the screen. Let's say we introduce one more statement here. And now in our call stack we have f22. And after printing it out, we are done with f22. So this is going to come out of call stack. So we finished executing f2 as well. So now we are executing f3 call directly from main. So let's name it as f3.2, because this is the second time we are calling f3. And it has parameter node n. It's not a primitive type. So what we are going to do is we are going to copy the value. We are going to copy the reference. So here we have n pointer, and the n pointer is going to point to the original memory location. Once we call n data plus plus, once we execute this statement, this is going to be 102. And then we are going to print it to the screen, and we are going to print 102 to the screen. Let's say this is the continuation of the screen. And since we finished executing f3, after printing it to the screen, we are going to get rid of, like we had f33, f32 here. We are going to get rid of this state. And this is going to be out of our call stack. And once we print b data to the screen, what are we going to print? 102. And once we print, there is no data for it, it's a primitive type. Once we print a to the screen, what are we going to print? 5. Like as you see, with the primitive types, even if we make some modification, these modifications stayed in the function. Like with the help of this plus plus, we were able to write 6 to the screen here. But as soon as we are done with the function, that manipulation is gone, because the manipulation is done on a different place in the memory. However, in the case of having a node object, since we pass the pointer by value and just copy the pointer, and both the input and the original variable were pointing to the same memory location, our modifications on the value, they stayed. And when we write these data inside of main, we actually see that we see the new value. So, is everything clear about function calls and the way that we pass values and copy values for primitive types and complicated types? Any questions up to this point so far? Okay, cool. Like actually we have seen pretty much everything that is necessary for understanding recursion up to this point. Because recursion case is not much different than one function calling another. So if main is calling f1, f1 is calling f2, it's not called recursion because all the functions are different from each other. However, when a function calls itself, that situation is called as recursion. And this is a very powerful use of solving some problems, like basically converting our ideas into coding, because in some cases, recursion actually can make our job very easier, especially if it is easy to define our problem or solve our problem in terms of solutions of our subproblems. So, like the first common example that fits perfectly to recursion is calculating factorial. So are you guys familiar with the factorial operation in math? Like basically, Fn is equal to multiplication of numbers from 1 to n. Like this is multiplication sign, it's very similar to sigma sign. Like the sigma sign is for summation, right? So this is for multiplication. Like basically, pi I equals 1 to n, pi I is equal to pi 1 times p1 times p2 times p3 times pn. So, like if the definition of factorial function is like that, like first, let's write it iteratively. Let's say we are dealing with very little numbers of factorials, so let's say integer is going to be enough to fit the result. So we get n as parameter. And then what we are going to do is I is equal to 1, or we can even start from 2. I is less than or equal to n, I plus plus, and let's say we have result that starts from 1, and we say result multiplication equal to I, and then we return result. So this would do it if the result fits in integer, right? Yes. So now let's look at the recursive version of the same function. So there are two things that we should be careful with recursion. The first one is which subproblem solutions are needed for the current state solution. So here we want to find factorial n, right? So which subproblem is going to be very useful when it comes to calculating factorial n? N minus 1, right? If we know the answer for factorial n minus 1, we can just multiply it by n, and then we can have the result. So here, we know that if we have the answer for factorial n minus 1, we can just multiply it with n, and then it will be our result. So that's the first part that you should know when you are using recursion on a problem. Which subproblem solutions are useful for us, and how we are going to generate the solution for our current state based on those subproblem solutions. Okay? And the second point is, like basically in recursion we make a deep dive on something. Like we go deeper and deeper and deeper and deeper. What are we supposed to do? At some point we need to stop. Right? So, the second important part of recursion is deciding on the base case. Like it is called base case. When are we gonna stop? When are we not gonna call subproblems anymore? Where did we start from? And in the case of factorial, like we can define it as, let's say if all the input are positive integers. What is going to be our base case?
N equals to 1.
Right? If n is equal to 1, we know that the result is 1. So, now let's see what is going to happen if we call fact or fact r functions. So let's modify our main. Let's get rid of these guys. We forgot the return 0 here. Let's just put it. Okay, so let's say first we are calling fact. Five. And then we are calling fact 5 with, fact R5. So when we call the fact function, what is going to happen? Right now we are in our call stack, right? So we have the main function. Let's say we start executing again. That's why I'm going to name it as M1. Do we have any variables inside of main? No. So there is not much that we can represent in the main function state right now, so I'm going to skip it. And it's calling fact5. So basically we are calling our fact function for the first time, so I will represent it as fact1. And what are we going to have inside of fact1? We have one variable, n. And n is a primitive type, so what's going to happen is we are going to copy the value. So this is going to have 5 in it. And as we continue execution, we are going to meet with another variable, which is res. So let's make it a little bigger. So we have res here. And then res is going to have 1 in it. And then we have another variable actually, I. And I starts from 2, oops, I is going to be here. I starts from 2 and goes up to n, and it's updating results. So once we reach to the last statement in this function, the result is going to have 120 in it. And I is going to have 6 in it. Actually, since its scope is just this loop, it's going to be gone once we reach to this statement. And once we return res, this value is going to be printed to the screen. So let's clean our screen up. So we are going to print 120 here. And we will be done with the function call, right? So this fact1 is going to be removed from the call stack as we return from the function. And after that we are going to print it to the screen, and we will be again in the M1 state. Then we will continue with the next statement, which is execution of fact R. So also we are done with this guy. This is the first time we are calling fact R. So I will represent it as fact R1. And we have one variable n again. Oops, here, n. And it starts from 5. So is n equal to 1? No. Therefore we are going to skip this part. And in the return statement we actually make another function call, which is the same function. So I'm going to name it as fact R2. But this time we call it with a different input, right? So let's place fact R2 here. So this time what is n? 4. Again, it's not equal to 1. We get to the return statement. And this time we actually make another call to the same function. So we have fact R3. But this time we call it with n minus 1, so the n value is going to be 3. And we make another call again, n is not equal to 1. This time n is equal to 2. And for 2 again, since it's not equal to 1, we make another call. Here we have the fifth fact R5 state, in which we have n, and this time n is equal to 1. Since n is equal to 1, in the execution of this function, this time we are going to go into this if statement. And we are just going to return 1. Once 1 is returned, like you can think of whenever we make a function call, there is a hidden box that is created for the previous function call. So once main calls fact R here, like in the box of M1, like we have a space for the return value of fact R5. Likewise, after we make this call and fact R1 made call for fact R2, so here we will have fact R2 box. Here, fact R3 box. Here we have fact R4 box. And here we have fact R5 box. And once we are done with the execution of fact R5, what we are going to do is we are going to return the calculated value, which is 1 in this case, and then write it to this box to be able to continue execution of this state. And now we are done with fact R5 in the call stack. So we are back to the return statement. And sorry, this was not 5, this was 1. 1 is returned. So now we can continue with the execution because the value is calculated. So we basically multiply n with fact n minus fact, this is fact r, right? Oh, I have a typo here. Fact r n minus. So, like since both variables are available right now, we multiply them, the result is 2, and then we return it to our caller. So 2 is written here, fact R4 is now out of call stack. And now we have all the variables ready for fact R3. And then we make the multiplication, 3 times 2 is 6. So we return 6 to our caller, and we get rid of this. So 6 is here. Now we make the multiplication, 24, and then we return 24 to our caller, which is fact R1, and then we get rid of this. And then this goes out of the call stack. And here, fact R1 again have everything available now. Then we make the multiplication 5 times 24, we have 120, and then we return 120, take this out of call stack, and then write it here. And finally, we get back to the main function. Like even fact R1 is gone now. And since the result is ready available, we just print it to the screen. And we are done with the execution. So here, we execute return 0, and even M1 is out of call stack now. And since we are done with the main function, there will not be any call stack anymore because we are done with the execution of the program. So, were you guys able to follow it from the beginning to the end? Like, is everyone clear with how recursion works? It's not much different than any other function call that is made by one function. So once the function calls itself, we call it recursion. But in the implementation of recursion, there are 2 points that we should be careful with. The first one is, which subproblem solutions are going to be useful for us when we are building solution for our current state. So in the case of factorial, we said, if we want to calculate fact n, factorial n, then the result of factorial n minus 1 is going to be actually very useful. So that's why we refer to that. That's the first important point for recursion. And the second important point for recursion is deciding on what is our base case. Because, like, basically we are making a deep dive. We are going deeper and deeper with our calls. And at some point we should stop. And that base case actually defines where to stop. In the case of factorial, we know that factorial 1 is 1. So we don't have to go deeper after that point. That's why we tell our function with this statement that, hey, if you reach to 1, no need to call yourself again. This is where you are going to stop. And if we have these two properties, then it means we can use recursion very effectively. So, but there is one thing that we have seen, different behavior when it comes to executing fact and fact R functions. So, in the fact function, since there is no function calls, whether it is for itself or another function, we didn't really make use of call stack much, right? We were able to execute everything within the boundaries of the function inside of the state of the first call of fact function and return the result. However, in the recursive version, every time we make a call, we actually introduce a new state and then put it to the call stack, right? So the first problem that you can have with recursion is this call stack actually has a limited memory. Meaning, if you make like tons of function calls again and again, at some point you can get stack overflow error. Because you will reach the point where there will be number of items that is more than the call stack can handle. Like for example, we already worked with big numbers, right? We have multiplicators for big numbers. Instead of making this integer, if we return an array, then we can actually make our factorial method support very big numbers, right? By using the function that we had developed at the beginning of the course. So, let's say with that implementation, with this function, we can easily calculate factorial 1 million. Would it be fair to say? Because even 1 million doesn't have many digits. Our multiplication algorithm complexity was depending on number of digits in the number, right? So 1 million has like 7 digits. So it's not going to be that much. Any objections? Yes?
We continuously multiply them, so we're going to have bigger and bigger numbers.
Yes.
So from at least 1 million to say 100,000, we'd have almost 900,000 7 digits, multiply those, and we'd have over nearly 1 million digits.
Nearly 1 million digits? Okay, so that's fair enough. Let's say instead of million, 100,000. So it's going to be reasonable. If we make fact call with 100,000, we can calculate the output comfortably. It's going to be okay. But if we do the same with the fact R function, still using the same functionality we have for multiplication, we are going to be putting like 100,000 objects in the call stack. And depending on the limit of your computer, you might actually get stack overflow error. Or let's say this wasn't about multiplication, but we define another function in which we just do the summation. We increase it by 1. With one for loop, we can easily iterate on it, right? But if we do the same thing with recursion, again, since we are putting too many items in the call stack, we have the risk of getting stack overflow error. So that's one thing, like basically if you get stack overflow error, the execution finishes at that point and like you basically have runtime error for your program, okay? So that's one thing that we want to avoid for sure. And the second problem is, even if let's say you have enough space in the call stack that you produce the answer correctly, because of every function call creating a new object in the call stack, it actually brings some new overhead. Like when we are calling a function, as you remember, we were copying values for the parameters, like creating a new object in the call stack and so on. So actually a function call is not for free. Like there is no free lunch. Likewise, here we need to pay the price if we are using recursion or if we are making any function call. And with recursion, the price can actually increase very quickly. Because if it's just a function call, if there is no recursion, then it's going to be hard to have like 100,000 function calls, right? Unless you're writing the program with the help of the program. Even in that case, some languages actually have some limit on the size of the source code. So without recursion, it's going to be hard to hit to the boundaries of call stack. But with recursion, we have this risk. So keep in mind, know that the recursive version is not going to be as efficient as the iterative version. But for many problems, recursive solution can be way cleaner than the iterative solution. So sometimes, for the sake of readability or for the sake of ease of implementing solution, you might choose recursion over iteration or iterative version of the code. So one question. Do we have some type of problems which can only be solved recursively? Looks like nobody has confident opinion, so let's vote. Who thinks there can be a problem that can only be solved recursively? Let me see hands. Then you guys actually have confidence. Okay, so why do you think otherwise? Oh, you're not completely sure. Okay. But actually, if we apply wisdom of craft here, we won by a big margin. So many people think that there are no such problems, and that is true. The reason is, like in recursion, there is no magical thing happening. Like everything is happening by using the call stack, right? So call stack is just a stack, as we see in previous lectures. So you can basically simulate everything that you can do with recursion by using a call stack and just simulating all the operations. So instead of the function call, you can push a state into this stack and then pop once you are done with the execution and use the value that comes from the stack and continue with that one. So unfortunately there is no magic happening in computer, but the good news is, let's say you implement something recursively and you don't get the performance that you wanted, so you can think of, okay, so how am I going to implement this iteratively? Because that way, if you implement the same logic iteratively, you're going to get some performance improvement, basically. So in general, if you see that the both solutions have the same difficulty in terms of implementation, the recursive version and the iterative version, I would suggest going with the iterative version. Likewise, at the beginning, once you are solving things with recursion, at least think about how you can do it iteratively. Because not all the problems have the same difficulty when it comes to implementing it recursively or iteratively. Like some problems, they are going to be super easy implementing recursively. So let's take a quick example of it. Like you guys worked on writing a prefix calculator, postfix calculator in previous lab sessions, right? So everyone is familiar with the prefix format, postfix format, and infix format. So let's take an example of an expression. And since the easiest for us, for humans, is infix, let's have our example in the infix form. Let's say we have does anyone have a board marker? No? Okay, slightly, okay, it's better now. Let's say we have 6 times 5 plus 3 minus 14 over 2. I'm just going to put parentheses for being clear on distance. And first we are going to start with multiplication. We have, no, it means we are going to start with plus. And on the left we have multiplication. On the left we have 6 and 5. And on the right of the plus we have 3, of course. And we have minus. Right. We have 14, 2. Like basically this infix expression can be represented in a tree like this, right? So let's say we want to convert this infix expression into a prefix expression. And let's assume we already created the tree. And like root is pointing to the top, to the root of the tree. And we want to just print the prefix representation of the expression that is included in this tree. Like we have node root as our parameter. Or let's name it as node because we are going to make recursive calls. So it's not going to be root all the time. It's going to be root of the subtree, but it's better to name it as node. And in the pre-order traversal, what we are doing is first we print ourselves. And then our left children, and then our left subtree, and then our right subtree. So with this logic, we come to the pre-order traversal, and we have the node. Who are we going to print the first? Ourselves, right? So we will say we're just going to print the data. And after that, if we have a left child, then we are going to just call pre-order. Node left. And if we have right child, oops. Then we just call the same function with node right. And that's actually it. Like, as you see, this is very clean. The logic is very obvious. Whenever we are called with node, we just print ourselves first, and then we make the call to print our left subtree, and then we make the call to print our right subtree. And let's say we want to change pre-order to in-order. What are we going to do? Just change the order, right? Instead of writing us at the beginning, we are just going to write us between right and left, and it's going to be in order. And in order to make it post order, again, all we gotta do is to change the order, right? So if we print ourselves after everything, then it's gonna be post order. Like, if we did the implementation iteratively, then switching from pre-order to in-order or from in-order to post-order, I don't think it's going to be this easy. So, and like here, for example, the difficulty of all three types of orders is equal, right? It's the same code, just the order is different. But as you will see, when it comes to doing the traversal iteratively, like the post order might be a little more challenging than in order, for example. All right, so any questions up to this point so far? Now, once you think of the binary tree and binary search tree problems you have on the list, do you guys think that recursion is going to be useful for many of those? Right? So, let's focus on the binary tree and binary search tree problems for the training session today, for the lab session today. And for tomorrow, I'm going to add some recursion tasks as well. Okay? And if you have any questions, please feel free to ask to me.